talking about, to try to talk about two topics. The first being contextual bandits, which is a nice lead-in into reinforcement learning, which you'll hear about from Emma next week. And then we're also going to cover very brief introduction of adversarial bandits, just to give you a flavor of what that looks like. So in contextual bandits, so one of the problems that I mentioned in introducing these lectures was people showing me to a website, and you go around the internet, and there's information that we have about you. Say like where your IP address is located, just your physical location. We have maybe your past viewing history. We have maybe your demographics, these sorts of information. And all of this can help us provide you a better recommendation or show you a better ad or so on and so forth. Or in a medical situation, we have your past medical history, and that can inform, given new symptoms, what is the best treatment specific for you. We call this problem contextual bandits. And how it works is that, for times t equals 1, 2, etc., nature reveals a context and for the simplest, just for simplicity, in this lecture, I'm going to assume that contexts are drawn IID from some distribution. So this could be just say like some vector in RD drawn from some IID distribution, some stationary distribution. That assumption can be dropped, but just for simplicity, we're going to assume that today. And now the player, or the algorithm, chooses one of his arms, is xt in, I don't want to do that. xt in x, where this is his known set of arms. These could, again, be feature vectors, or they could just be an arbitrary set, like 1 to n. And then nature reveals some reward, which is equal to, I'll notate this as v of ct xt plus some noise term. And so the player can, when he chooses xt, he gets to see the context. So he'll see, say, your medical history. Given your medical history, he will make a particular choice of treatment, and then nature will reveal whether that treatment worked or not, whether you survived or not, sort of thing. As typical, X is a known set. It may have feature vectors, some like just in the linear bandit setting, so that they have some sort of context with each other, or distance or metric with respect to each other. But it won't really matter too much for this case. And then eta t, of course, is some IID sort of noise sequence with mean 0. And I'm going to assume for the purpose of this lecture that it's even bounded. Say it's like absolutely bound between -1 and 1. But again, these assumptions can be loosened. It's not that big a deal. It just makes it very simple to have this very sort of rigid setting of IID contexts and IID rewards. Okay. So given this, you might be wondering, what can we do? So the first, in line with what we did last time, this whole linear bandits setup, it turns out we can actually reduce this setup to linear bandits, or something very close to linear bandits, in the following way. Define a feature map So in linear contextual bandits, we make even stronger assumptions than this. We say, assume there exists a feature map phi that maps context cross arms to some vector in Rd. And V Cx, or for all Cx, is equal to the inner product of this feature map of Cx theta star for some unknown theta star in Rd. So this is a very strong assumption, but it's extremely common. So what it's saying is that in linear contextual bandits, this is the more general problem, which we'll return to in a moment. But in this simplified setting, we're saying, OK, for any context in any arm that I have, there exists some function phi such that I map to some high-dimensional space, perhaps. I take the information I know about x, the information I know about the context, I map to some feature space. And in that feature space, there exists some theta star such that the value of the reward, the expected reward of showing arm x with respect to context C is just the inner product between phi of Cx and theta star. The most common sort of way of representing this is kind of strange at first, but one of the simplest feature maps is just to do polynomials. So like, let's say C and X are both in, say, Rp. So like example, X is vectors in, say, Rp, and C are vectors in, say, Ro. Now let's say Q. I don't like O. Rq. Then we can have that phi Cx is just equal to the vectorization of x C transpose. And by vec, I mean like xc transpose is a matrix, and then vec is just doing some arbitrary way of vectorizing it. Say just like taking the columns and just stacking them on top of each other so that it's a big vector in R P Q. This seems kind of strange, but it's actually very intuitive once you start thinking about specific cases. So if you have no sort of information about your x's, you can say your x's are just the canonical vectors. That's how we mapped the linear bandits problem down onto the standard multi-arm bandit problem. And then what this mapping is doing is it's just saying, it's the equivalent to saying that each arm has some unknown theta vector that, and so when a context shows up, I'm trying to figure out what is the unknown theta vector associated with that arm that has highest inner product with the context. Going through examples like that actually makes this very natural, and this is used very, very, very frequently in practice, either with the context being individual sort of canonical vectors, or the x's being canonical vectors, or them being both arbitrary and using other feature maps like random feature maps, if you're familiar with these, like random cosines and things. Yeah?
Could you explain what you meant by if that becomes a theta vector? It's not theta star. You just mean a different arm.
So what I'm saying is that if the x's are the canonical vectors, then the way that you can interpret this is that, or one way to interpret what's going on here by doing this feature map, is that each x, each of your arms, is associated, because now they're orthogonal, with its own feature vector. And it's just an unknown feature vector. And you're trying to learn this feature vector by playing different arms. And so it's kind of the reverse linear bandits game, where now each arm has its unknown theta star, and you're trying to sort of play these arms in such a way in order to learn this unknown theta star. it makes sense if you, it's easier if you just go through this example on your own. We can talk offline later, though. Be happy to. And so, okay, so this is a very general setting. And this feature map could also, instead of being like that, like polynomials or something, a lot of times, and most frequently, this feature map is actually just a deep network. So what you'll do is you have some historical data. You've seen what's happened when you've shown this action or this arm with this context and got some output. And so you learn some deep network. You just use the last layer, and then you use the features from that last layer for any input context and arm to run something like this. And this is precisely what that shop by look thing that we're doing did. It was this bandit setting. Yeah.
Then by last layer, what you mean? Because usually in practice, people put a softmax layer at the end and then select the winner. Then you mean removing softmax layer and use a multi-arm or linear bandit algorithm at the end?
Yeah, precisely. So like you just remove that last softmax and just use those features that are there. Yeah.
Follow-up to that. So what are these deep networks being trained towards? What's the loss function?
Oh, so typically it's like it could have been rewards for some other process. So like they have, you were giving some context and some action, and then you observed some signal, whether it was signing up for some mailer or clicking on something. It doesn't really matter what the task is, and this is where like multitask learning really comes into play here. You really just want those features, because if the features were useful for this task, they're probably relevant for some other task as well. Okay, so this is linear contextual bandits. It's very much used in practice. It's very useful. However, it's an extremely strong assumption because the core difficulty here is you have to design this fee, and that can be kind of tricky sometimes. And so what we can do is we can actually get a little more intelligent or define something more general for the contextual bandit setting that then will tie back into what Rob spoke about in statistical learning theory. So in that vein, so general setting, general policies. So a policy is a map pi. Policy pi is a map from context space to action space. Right? You see a context, and then you map it to whatever action you're going to take. And what we define the value of a policy as being, under this IID setting, the expected value of the context being drawn from D, the noise, this is an eta, as V of context pi context, plus this noise, which is zero mean, so it actually goes away. But I just wanted to make clear that this is the noisy reward or stochastic reward. Okay, so that's what we call as the value of the policy. And at each time t, we're going to be playing some action xt, but we're going to restrict ourselves only to actions in which there exists some policy that would play that action. Okay, this is pretty much without loss of generality, because if no policy in your policy class would choose to play that action, then you probably shouldn't be playing that action. And so what we define the regret after t time steps as being to t times the value of pi star, which is going to be the best policy, minus the expected value of t equals 1 to t of the value of pi t, where pi t, like I said, in this general setting, I'm playing an xt, but without loss generality, I can say that I'm actually playing a policy pi t at each time. And then that policy is choosing xt with respect to ct. Okay? Maybe. Okay? Is that clear? Where pi star is, of course, argmax pi in big pi of v of pi. And this big pi is just a finite class of policies, let's say. We can extend this to infinite classes with VC dimension in the usual way, but let's just think about finite classes for now, where it's just some set of functions that maps context to actions. And in this setting, now we're totally general. So the policy classes can be anything. They can be, multilinear regression. They can be neural networks. They can be boosting. They can be anything. And they often are. Boosting is not uncommon in this setting. So then what we want to do is the main challenge in contextual bandits turns out to be that unlike in multi-arm bandits, at each time I could play any action. And when I play that action, I'm going to get a reward at this time. And if I play that action 2 time steps from now or 3 time steps from now, I'm going to get the same IID action. And so whether I play the action now or in the future, I'm getting the same amount of information about playing that action or arm. And so it doesn't really matter the order in which I play the arms as long as I play all of them the same number of times. When we move to contextual bandits, that's no longer true. And this is where the core difficulty comes in, because if at this time I see a particular context and I play some particular policy or take some particular action, that very much means that I did not take some other action with respect to that context. And now you're in this situation where you don't know what would have happened if you would have played some other action. All you get to see is your history of what action did you play in response to which context. Okay? And this is actually a very, very big deal for actually training these things offline. And so while in Bandits I could do sort of uniform exploration and in an offline setting and then figure out what was the best arm and then just play that arm forever, say if I was in pretty bad bandit algorithm, but it would work. In this setting, that's no longer possible. Because if I with respect to each context, I might want to take a different action. And I can only take one action with respect to each context. And if these contexts are from a continuous distribution, it might be that I'll never see the same context twice. So how do we deal with this? And what do we deal with this is inverse propensity scores. So what we're going to do is I'm going to define an estimator. So I want to get an estimator for each pi, what the value of that pi is. Right? I want to build an estimator for v of pi for every single pi, regardless of what actions I take. And the way that I'm going to do that is, suppose I have a distribution mu, which is a distribution over actions given context. So this is my, in the simplex, over arms, over actions, okay? And I'm going to assume that I have a finite set of actions. And what it's saying is that for every given context, I could have a different distribution. And so the context actually indexes this distribution. And this mu could be continuous. It could be with respect to the context space. It doesn't really matter. I'll define exactly what I mean by, I'll give you an explicit distribution in a moment. But the way that I'm going to build an estimator is I'm going to say that, and let's say I'm just going to, at every single time, I'm going to play action X with respect, when I see context C, I'm going to play action X. So like, play action xt with probability mu of xt ct for all t. Right? I'm going to play this policy for some amount of time. And then what I'm going to do is I'm going to build an estimator, v hat, of ct x is being equal to RT, indicator that XT is equal to X over mu X CT. Okay? So at each time t, I'm going to see this CT, the context CT. I'm going to play action XT. I'm going to sample action XT from mu. So maybe it'd be better to say like play action xt drawn, distributed according to this distribution mu of x given ct. So xt is a random quantity. And then I'm going to construct this estimator for v of cx, which is just a function. V of cx is just a given function for any context and action. I don't know it, but it exists. And I'm going to build an estimator for it for any cx as being equal to this. And then, why would I want to do this? Because then I'm going to build an estimator of v hat of pi as being equal, after t time steps, being equal to 1 over t, s equals 1 to t, v hat of ct pi of ct. I guess I should have little subscripts, although it's not super important. Okay? And what this will allow me to do, if I do this, because this is now a function, this v hat of t is a function of x. Right? The ct is fixed. This is like a historical record now. The ct is fixed, but then for any x, I can estimate this quantity. And so now I can start to talk about, well, for any given policy, I can now evaluate this. And what I'm going to claim is that this is actually this is a fine estimator. And to show you that, the expected value given some context ct, so we're at time t. Well, the only thing random here then is xt, what xt was chosen. Well, actually, there's two things that are random. The xt that was chosen according to mu of x given ct, and rt. And again, rt is a noisy but unbiased estimator or version of v, the true v of cx. And so what we have is that this is just, I don't know what the x prime is, so I'm going to sum over all x prime. And now we have that this is RT indicator xt equal to x mu of x given ct, just plugging in this estimator. But now it's given ct and xt equal to x prime. Okay, so I'm just taking the expectation with respect to x prime. So this is given x prime, xt is equal to x prime, and this is the probability that xt is equal to x prime. So it's just the law of total probability. Yeah.
So in this equation, v hat t of ct and x, you're putting an indicator for xt equals x, but what if you didn't observe that, right? Then you're just going to have a 0 there.
Yes.
But is that 0? I mean, it's not that you think the reward is 0. You just never took that action. You don't know the reward.
Yeah. Hold that question for a moment. I'll get back to that. You're absolutely right. You will get a lot of zeros. Yes.
Your definition of b hat t of pi, you have some s equals t to 1, but then you have no s's in here. Or should all those t's be s's?
Yes. Thank you. Thank you.
Is that like bold S there, SX there, is that the sphere or?
Sorry, this is what you're denoting as a simplex. X in 0, 1.
Then xt is the observed x based on your historical data, and x is all other x in RD in the space, or?
xt is the one that you drew from, is the random quantity that you drew from the distribution mu of x given ct. It's the one that you actually played. This action, I'm being rather abstract with it. It could be a vector in RD, or it could just be like it's this particular x that I drew. Yeah.
And like in the simplex, you mean like a lambda, just to not have another x.
Sure. Yeah, it's a dummy variable. Yes.
So here you're playing policy pi or policy mu, or you're playing policy mu and you're comparing pi to mu.
One and the same, in some sense. It's basically, I could say that my policy pi is actually a randomized policy, which is mu. So given ct, I'm going to play xt drawn from mu, and so it's what will happen is that I'll actually be playing a distribution over policies, and this will be a draw from that distribution.
So we are assuming E is finite, X is finite, and like mu is lower bound.
Yes, I'm assuming that x is finite, x finite, and I am assuming that for all, I was going to get to this, but is greater than 0 for all xc.
E could be infinite.
Where's E?
The set of all numbers.
C, script C. Script C could be infinite, yeah.
No, I mean E, because you said you draw CT from some E, right?
CT from some distribution D? Yeah, CT could be continuous. It could be infinite. There's no restriction on that.
Is the assumption that mu is positive necessary? Because if
Yes.
mu is 0, then I never take that action, right?
Yes. I'm going to get to this in 1 second. I just need to finish this calculation, and then we'll get there. So given ct and xt is equal to x prime, there's nothing random inside this. The only random thing is the RT. Okay? Because ct and xt have been fixed now. And so the only random quantity inside this expectation is RT, but the expected value of RT is equal to v of cx by definition. And so what we get is that this is just equal to because x prime, this is only on if x prime is equal to x. So I could put mu of x or x prime here because it'd be 0 otherwise. But now we get cancellations because this is the same thing as this. But then this guy, if you're summing over all x prime, you're only ever going, this is only going to be on if x is equal to x prime. And so then this is just equal to v of ct x. Yes?
So here, in order to have an unbiased estimation, you have to do this equal to this standpoint. But this mu of x and ct can go very low and close to 0.
Yes.
Give you very large variance.
Yes. Hold that question. So the big takeaway here, though, is that for any x, this v hat ct of x, this estimator, is an unbiased estimator of the true unknown v of ctx. Okay, so for any x, I can plug in to this, and that will be an unbiased estimator of this. However, what was pointed out was that, wait a second, this is going to be 0 for all x not equal to xt, which seems weird. And then when x is equal to xt, I'm boosting it by this probability mu, which is going to be less than 1, which could be massive. 1 over that number could be massive. And so, but what we're really doing here is by using this idea of inverse propensity scores, and this mu is the propensity score, the proportion of times or fraction of times you'll see that. And so it gives you an unbiased estimator. I mean, the math works out clearly. But it could be extremely high variance, because most of the time it's going to be 0. But then when it's not 0, it's going to be enormous. So the expectation is an unbiased estimator, but the variance is very large. And if we go through this same calculation, we can also, so just as a comment, we also have the expectation immediately by the linearity of expectation is equal to v of pi. Okay, so because it's just summing them up. And so what this is saying is that we can now, once we've seen many, many time steps of this policy, we can actually estimate the value of a policy pi for any policy pi, an unbiased estimate of that, just by doing this. And note, what would we need to do? What do we need to actually build this estimator? We need to log some things. So for each t, all this estimator requires is ct xt, what action did you play, rt, what reward did you get, and most critically, mu of ct xt. For all t equals 1. So what this does is it demonstrates what you would need to do if you actually went to go implement this system, say on a new website or something, or at a doctor's office. You need to log what context you saw, what action you took, what reward you got, but most importantly, you need to log the probability of what it took to actually take that action. So there was some probability that you took that action, and you need to log that. And that's critical to this stuff. And if you don't log this probability, or if this probability is 0, then this will no longer be an unbiased estimator. Yes?
When you say need to log, I mean, you're the one who's choosing what mu to take. So this is, like, you're saying this in this sort of data acquisition step. Like, you first of all do this, and you write down which mu's you take, and then later you can put it into some algorithm to generate a meaningful policy?
Yes, but these probabilities need to be logged. And this, I know this sounds stupid, but like this is a major issue in practice.
Forget to save the probabilities, and then they don't know what to do?
Yes. Very, very much so. Okay. So, as was alluded to, this is an unbiased estimator. But what you can show by doing the same exact calculation, if you look at the variance of this estimator, v hat t ct x minus the expected value of that guy given CT squared, just the variance. This variance, turns out you can show, is less than or equal to 1 over mu of x given CT. Meaning that as mu gets very small, the probability of taking any action gets very small, your variance for this explodes. So you have to be very careful. You can't just let these probabilities go to 0. You have to keep playing actions even if you don't think they're doing so well. But you still have to balance this idea of exploring, putting enough weight on all your actions, with exploiting of I want to actually get high reward policies. Okay. Now the big sort of reveal now is how do we actually do this? So what I'm going to do is let Q be a distribution over policies. So it's going to be a distribution over policies S big pi. So this could, big pi could be an enormously large set, by the way, like uncountably large. But no, it has to be countable. And let's just say it's finite, but it could be very, very, very large. And now what you're going to do, for any fixed distribution Q, when you play at each time, you're going to find mu of x given C as equal to x such that pi, pi in pi such that pi of C is equal to x. And that is the probability in which you're going to take action x. So you're going to fix some probability distribution Q. And then you're going to do this. And so now, what we just said a moment ago is that the expected value of v hat, the expected value of the value function, estimator, is equal to the value function. What that means is that v hat is an unbiased estimator of v, but it's also the least squares minimizer. And so what we're going to do is do our action elimination step. So we're going to have the same action elimination algorithm, except for at each time, just as we tried to pick a distribution in standard multivariate bandits to equalize the confidence intervals of each action. And then for linear bandits, we did the same thing. We tried to find some distribution over the actions using G-optimal design in order to minimize the maximum confidence interval of playing a particular action, or minimize the confidence interval of our uncertainty about taking a particular action. We're going to do the exact same thing here. And how we're going to do that is we're going to, at round L, choose a distribution Q hat L that minimizes argmin Q max pi in pi hat L. So we're going to be having an initial set of policies and start removing them just as we did in all the algorithms that you've seen in these lectures. And then minimizing the variance, an upper bound on the variance. Which is, of course, this quantity can be lower bounded, or can be upper bounded by just looking at these variances. Even though we don't know what the true value function is, we don't have a closed form on this variance, but we do know it's upper bounded by this inverse propensity score, and that's exactly how we're going to choose our next Q. For technical reasons, we're also going to inject a little bit of uniform noise into it, meaning that with probability gamma, we're going to take some random action, just for technical reasons. But basically, this is what we're going to do. We're going to proceed in rounds. At the beginning of each round, we're going to look at our history of all the pi hats, this set of policies that we're still considering. We're going to define some distribution Q that minimizes the maximum variance of our estimates, just as we did for all the algorithms we've seen, just like G-optimal design. And then for that round, for tau L time steps, which is defined basically in the exact same way that was defined for linear bandits, we're going to play a policy according to this distribution over Q. Yes?
I'm a bit confused. So when you say argument over Q, where does Q appear in the expression? I'm sure it's implicit somewhere.
Yes, it's implicit in the fact that this Q is going to define this, mu, and then this thing is going to be, this is an upper bound on the variance. And so that's how these are connected. Is that clear? Because for any Q here, that defines a distribution mu of xc, and that distribution mu of xc is 1 over that is an upper bound on the variance, which is exactly the thing that you're minimizing. So these things are, it's a program that you have to sort of like just put inequality constraints on. Yes?
And at each round, the dimensionality of the simplex from which we're taking big Q is reducing, right?
Exactly, yes.
So it should be QL, argument Q sub L or something like that, depending on the round.
Yeah. Exactly right. But that's sort of the beauty of this. And the reason why I structured the lectures as I did is to sort of demonstrate that this is sort of an algorithmic trope. That to solve bandits, like one possible algorithm that gets nearly optimal rates in a minimax sense is to really just play G-optimal, successive stages of G-optimal design. Of at each stage L, I want to define some distributions over actions such that I minimize the maximum variance of the possible actions that I'm still considering. And that's exactly what this is doing, it's exactly what linear bandits did, and that's exactly what the standard multi-arm bandit algorithm was doing as well. And just for good measure, if you do this, you can get a regret bound that looks like RT less than or equal to, I lost it. Square root of T x log pi T over delta. And then, of course, that's with high probability, probably 1 minus delta. When we do our trick with delta equals 1 over t, this goes away, and we actually get our RT. Because, yeah, just as we did before. And so this is pretty remarkable. Basically, the number of policies only enters into the log, just as we saw with Rob's finite class bounds and VC bounds and things like this. And these can be, those VC ideas can be extended here as well. Yes, there exist efficient computational algorithms to actually do this. I'll add some of those to the notes that I'll post later. Okay, any questions about this? Yes.
So you mentioned history as kind of an idea of the context, like medical history, but that's the time series, so you might have some autocorrelation. And in your policies, in that type of situation, you would probably want to consider like past context as well as the current context. And you might want to, and you could potentially exploit some understanding of the correlation structure of the context as well, right?
That's an excellent question, yes. So what she's pointing out is that, like, well, if you're coming to this doctrine multiple times, this context is actually changing over time. And it's a time series. And they're not just arbitrary. I mean, this assumption that the context of IID is clearly false. And that's absolutely true. And moreover, if at this time I take this action, I give you this treatment, that's actually going to change the context I see in the future. And this is precisely reinforcement learning. It's when you can think of states as being contexts, and if my actions can actually influence future states or future contexts, that is a reinforcement learning problem. Contextual bandits is sort of seen as like a baby reinforcement learning problem because I'm explicitly assuming that my actions do not influence future contexts that I see. And if that isn't true, then we need to go to a more Markov decision process and reinforcement learning setting, which Emma is going to talk about next week. And that's why I want to give you this sort of lead-in to that discussion. Yes?
Linear contextual bandits, is it similar to an SVM essentially?
Only in how a linear bandit is similar to an SVM. But I think the connection you're seeing here is this feature map for kernelization and things like this. If you're familiar with the kernel trick and basically mapping all your feature space through a feature map up to an infinite dimensional space or higher dimensional space where you can do efficient inner products, all of that can be extended to everything I've talked about in all of these lectures. When I say linear, basically you can always map this up to an RKHS where you're linear in that infinite dimensional space. It's from a technical perspective, there's not much more going on there, but practically it could be a huge advantage. And this is where this has motivated more practical algorithms, things known as like RKHS bandits or Bayesian optimization.
It seems like with the medical example, you maybe have a lot of ethical issues because you're playing these policies that are perhaps, you're saying you have to keep mu. You have to play the things that are kind of bad, right? So I mean, do people think about that in this context? And
yes.
Like, what would change?
Yeah. I've said nothing about fairness. I've said nothing about ethics in any of these bandit settings. This is a major concern. And there's not like a really great consensus of what it means to be ethical or fair in terms of algorithms. But for those definitions that have been written down, people have proposed algorithms that satisfy certain constraints like this. Yeah, I'll just leave it there. There exists a vast literature that's growing, but it's still much a very early field.
So, in the Bandits problems that we saw, where does the learning take place? Is it in the elimination of options?
Yes.
Okay.
Yeah, it is the elimination. It's that I've learned some base sort of knowledge about all of my policies and the ones I'm still considering, and then I'm eliminating those that are bad and only refining to the smaller set, and that is the learning process.
How does T depend on L?
So how this algorithm works is it's relying critically on the fact that these contexts are IID according to the distribution. And so what that means is that I'm going to proceed in rounds of L. And so at stage L, I'm going to define this distribution based on my history. Then for the next tau L time steps, for T equals tau L plus 1, 2, 3, etc., I'm going to be playing a policy drawn from Q. So each time T, I'm going to draw a policy pi T from Q and then play that policy. Yes?
And then in practice, how do you select Q, and is there any study that shows what kind of Q is efficient in conversion, or?
You choose Q to minimize this this optimization program. And this is we're minimizing an upper bound on the variance, which is a very naive thing to do. They're just more efficient procedures that can be done computationally more efficient. This, as written, is intractable. Okay, last question before I get to.
If you say somebody collected data using some policy and then they gave you the data but without the policy, without the probabilities.
Yeah.
Can you really not do anything at all? Like, is there a theorem that says you cannot do anything? Or?
I mean, in the worst case, you cannot do anything. However, typically things don't happen in the worst case. And so this is a field known as learning from logged data, and it's a field of intense interest, a very active research, because people often do not log probabilities. Yeah?
Can you just estimate the probabilities from the data?
Yes, that's typically what people do. They make a model assumption and estimate the probabilities. Okay, I have to move on though, because I have 10 minutes and I really want to get to an overview of adversarial bandits, or just an introduction of the problem itself. Okay. Okay. So, in adversarial bandits, also known as non-stochastic bandits, we have no assumptions on how the actions or how the rewards are actually generated, other than they're bounded in 0, 1. But we call it adversarial bandits because we are assuming that the adversary can actually look at your algorithm. The adversary knows your algorithm that you're going to play. And then based on your algorithm, he's going to choose a sequence of rewards. He's going to choose some matrix of 0, 1, n times t. So if he's going to choose all of his rewards in advance of the game, and then you're going to play these rewards. And your objective is to minimize regret as usual. Okay? The difference here, of course, is that in stochastic bandits, these rewards, if I played an arm now, I get the same reward if I played it in the future, an IID response. Now, we actually have this same exact issue as we had here. If I play action 1 at time t, that means that I did not play action 2 at time t. And therefore, I did not see what reward I would have gotten if I did play action 2 at time t versus action 1. And so what that means is that I need to somehow predict what would have happened if I would have played action 2 instead of action 1, the one that I played. The way that we do this is exactly how we used inverse propensity scores over there. We're going to use an importance-based sampling. And so before I do that, you should convince yourself that this algorithm, or this setting, any deterministic strategy will get linear regret. All right, just take a moment and think about why any deterministic strategy will get linear regret. And deterministic strategy means that the adversary can actually predict exactly what you're going to do in response to his rewards. So just sort of take 30 seconds and think about that. So one way he could screw you is if at time, he knows exactly how you're going to react to him. So he knows exactly the sequences of IT that you will play if your algorithm is deterministic. And so all he's going to do is he's going to put a reward of 1 on any action you don't play, and a reward of action 0 on the rewards you will play. And because you can only take one action at any given time, you can always get linear regret. Yeah, so proof by demonstration. And so that's unfortunate. But what that means is that we need to have a randomized policy. Randomization is actually necessary for these adversarial games. And we already got an idea of how we might be able to play against this adversary. So if we define x hat it as being equal to it equal to I over PIT times basically the reward that you got, x it t, where so at each time t, if your algorithm defined some probability distribution pt, and then you drew it from that distribution and played that, then by the same exact proof as we have over here, the same sequence of steps, for that given distribution, you can show that x hat it for all I is equal to xit, the true reward that you would have observed if you played action I at time t. And so this is great, because what this allows us to do is, even though we're only taking one action at any given time, we're going to be receiving some reward for the action that we got, but we're able to estimate the reward we would have gotten if we played any other action. This seems magical, but again, it comes with a price, high variance. And so what we need is an algorithm that can balance the high variance with also trying to accumulate as much reward as possible. And this algorithm is known as EXP3. And what this algorithm does is EXP3 stands for exponential weights for exploration and exploitation. And what it does is it maintains a distribution PT. And if you get if the reward you play gets a 1, then basically using these important sampling estimators, you're going to boost the probability on that action. And if you get a 0 or a small reward on that action that you played, you're going to decrement the action that you play on that, the reward on that action. Very similar to how boosting works. So in boosting, if you got the label right, you multiplied each weight of that example by 1 or by some beta. And then if you didn't, then you multiplied by e to the minus beta. It's almost identical to this situation here. And then at each time, you're going to draw IT from that exponential distribution. The remarkable fact here, though, is that if you play this algorithm, you can show that this regret is less than or equal to square root of nt log t. No, it's even better than that. Nt log n. And this is remarkable because the adversary was choosing rewards. Right? This is non-stochastic. I made no assumption about how these rewards are being drawn. And yet we're still able to obtain sublinear regret. Now, the first question you must have is, why did you just talk at me for 5 hours about stochastic bandits if we could have gotten this guarantee on the first day. And the reason why is because this will never get better than this, right? And in our log t, in our gap-dependent bounds, we achieve logarithmic regret, where in short times it would get square root of t regret, but in long times we'd get logarithmic regret, log t times inverse gap or whatever. And that's a benefit of playing these against these stochastic assumptions. And so in situations where we can make stronger assumptions, we get stronger theorems. And so this is the trade-off. The last thing I want to say about this is that here I assume that the adversary chose actions or chose rewards before the start of the game. You can also prove theorems about adversaries that actually adapt to what algorithm you're playing. So what sequence of arms you played up to time t, the adversary can then choose what rewards to give you at that time. And yet you can still, for an analogous form of the definition of a regret, which no longer makes sense over there, you can get something that's still growing like square root of nt, which is truly remarkable. And with that, I hope you've enjoyed this introduction to Bandits. There's a lot of great literature out there. There's some excellent textbooks. In particular, Sebastian has an excellent monograph from 2012 with Odiber. But in particular, Tor Lattimore and Csaba Csepesfari have an excellent book at banditalgs.com that has basically the latest results and is very sort of comprehensive. Okay, and with that, thank you.